is fossil, and around 10% is circular, with the different contributions that I mentioned before. And then in the business as usual case, we have an increase from around 56 million tons to more than 70 million tons, of which we believe that reuse can moderate that by around 15%, and then of the remaining around 60, slightly more than 60 million tons, we believe that 65% can be circular plastics. And the three key contributors: mechanically recycled plastics, chemically recycled plastics, and plastics made from biomass, with a very similar contribution to the total. We then also have CCU-based plastics that we see also as critical in the long run, but which will only contribute around 5% by 2050. But the others all in the range of around 20%, with biomass here a bit less than the other two vectors, mechanically and chemically recycled plastics, but certainly something that is absolutely necessary to reach those high percentages of circular plastics, and also net zero across the full value chain, so including also the end of life of plastics and the products made out of them. So we see here, if you look from 2021 to 2050, I've highlighted a little bit the biomass wedge. So we see a significant increase, a tripling practically from 2021 to 2030, another doubling from 2030 to 2040, and then almost 100% increase again from 2040 to 2050. And of course, this is just a scenario to show what is possible. This should not be taken as a forecast that you should build your investment decisions for your old age pension on, but it is to demonstrate that yes, it is possible, and to identify what is required to make it actually happen. And this is what I'm going to focus on then on the following slides, because if we look at here, cost efficiency improvements in our roadmap. And again, I have highlighted here the plastics made from biomass and virgin fossil production. So at the moment, the OPEX, the operating expenses of producing bio-based plastics are roughly twice as high as those of virgin fossil production. This is expected to decrease to a difference of around 18% in 2050. So something where we could say, okay, if we then factor in pricing of CO2 emissions, for instance, we are roughly at par and competitive. But this reduction in the cost of biomass-based plastics is not going to come by itself. This will only happen if there are significant investments, if capacity is built up. And then the question is, how do we build up that capacity if at the moment that material is hardly competitive with virgin fossil plastics? So what we see here in we see actions that are required both within our sector, the wider sector, not just what we as Plastics Europe represent, the resin manufacturers, but the whole plastics value chain. So here, all actors are asked to develop partnerships to secure circular feedstock, to explore new technology investments and collaborations. to shift to more circular practices through recycling and better design. So this is particularly for what is downstream to our sector. It's about scaling plastics production from biomass and then, of course, investing in capacity and partnering with technology providers. So this is what is required from industry. However, we also need a regulatory framework that makes this happen. And here, what we see as paramount is to create a market pull for circular plastics, and particularly for biomass-based plastics. So we argue very much in favor of minimum circular plastic content targets for key plastics applications. If you follow the discussions on the different regulatory files, SUPD, so for Single-Use Plastics Directive, Packaging and Packaging Waste Regulation, End-of-Life Vehicles Regulation. There is the discussion is focusing very much at the moment on recycled plastics, but we're also advocating for targets for bio-based plastics within the same framework. We need a framework that unlocks industry investments, and very closely related to that, we need to ensure that the European plastic system can remain internationally competitive and viable during the transition to this highly circular net zero economy that we see for 2050. Sorry, I've lost my red line here. So there, at the moment, we are very concerned that because of a number of factors, this international competitiveness is jeopardized, and this is many of these of the problems that we see are homemade and can be remedied with a reasonable regulatory framework. And then the last point I've put here, which is something very important, is acceptance of mass balance approach for biomass. So this is a very specific ask. But it is key. Maybe you're not familiar with the concept of mass balance approach, so I will quickly walk you through this. Let's start with a fossil-only production. So you have a process, you have a fossil input. What you get is an output that is also 100% fossil. So now consider that in that process you use 50% fossil feedstock and 50% bio-based feedstock. And then you may ask, okay, so why do we have to process this in the same installation? Why can't we use different installations? The reason for this is there are existing assets, and building now separate lines for bio-based feedstock only would be very capital intensive. And also it is very difficult to, at the moment there is not enough biomass available, particularly there's not enough demand for bio-based plastics to justify investments into a separate production line. And if I talk here about 50-50 fossil bio, that is just for illustrative purposes. In reality, the percentages are significantly lower. So in a case like this, we talk about drop-in biomass feedstocks. So what you get here as a physical flow is, of course, a output that is 50% fossil and 50% bio. And it makes no sense to try to separate that afterwards. That would only deliver additional environmental impacts. But the problem is that you may have a client. Well, you imagine you as a resin manufacturer. You have a client who says, "Yes, I'm willing to pay the additional price for bio-based plastics. So I'm willing to take off that 50%, and you want to sell him those 50%." But it's physically mixed with the rest. So in that case, we use then the mass balance concept. It's a selective attribution, where you say, okay, from this process, 50% of the output are categorized as being 100% fossil, and the other 50% are categorized as 100% bio-based. So I hope this explains what mass balance is and why we believe it is necessary. So coming to the conclusions, transitioning the European industry to circularity and climate neutrality will need all levers. There is no silver bullet solution to significantly reduce waste disposal and greenhouse gas emissions. And bio-based feedstock will be one very central solution to lower the greenhouse gas emissions of the plastic systems and to reduce the use of fossil feedstock. What is very important here, and I have not elaborated on this in the previous slides, is we need access to sustainable biomass. Because we're fully aware of the fact that using biomass can be very negative for the environment. And when we're talking about sustainable biomass, we support the sustainability criteria as defined in the latest revision of the Renewable Energy Directive. And what we also support is to diversify the source of biogenic carbon by further developing the use of second and third generation bio-based feedstocks. So in our view, it is necessary and it is possible to use different sources of biomass for the material sector. So including not only biomass-based streams, but also dedicated biomass production, that also biomass that is grown for use in the production of plastics. And then finally, of course, this is nothing that industry can do by itself. So we rely here on a collaboration with all stakeholders, and particularly here we need that regulatory framework that the policymakers have to define to make this happen. And that's it. Are there any questions? I will stop sharing my, no, I will not stop sharing my screen because we may want to go back. So please, Susanne, if you may,
yes,
moderate the questions.
I would do that. So far, Jesper from Novo Nordisk, he has a question. So please, Jesper, go ahead. I think you can have some really interesting discussion. And by the way, thank you so much, Alexander, for your very insightful presentation. It's clear to everybody that this is a bumpy journey and it's a transition period that needs all stakeholders, and there's no silver bullet solution to this. So we all have to join forces. And Jesper, please go ahead, ask.
Yes, thank you, Alexander. Novo Nordisk is a medical company, and we produce or deliver our treatments in plastics. So we are very much oriented towards Plastic Europe, and it's great to see this. Honestly, I haven't read the roadmap yet, but I will. I just had one thought. A lot of the current chemical recycling is coupled with production of fuels, synthetic fuels that are replacing fossil fuels.
Mm-hmm.
And that gives good economy, because then you can take in a lot of plastic waste, and you can produce some fuel and some new plastic raw material of crude oil. But you lose some carbon. How do we make sure that we get a new inflow of new carbon into that cycle to compensate for what we lost to fuels?
Okay, that's a very good question, and also a very complex question. I will try to give a short, concise answer to that. So, like with the overall topic of circularity and net zero, there is no silver bullet. So it's about further technology development to increase the yields. It's also, we have to see that chemical recycling is just one of the levers here. So there are others. So this has to do with mechanical recycling, for instance. So if a waste stream is suitable for mechanical recycling, you should go for mechanical recycling because the losses are much lower there. You only go to chemical recycling if mechanical recycling is not an option because of the composition. There are too many plastics mixed. Think about plastic packaging. You probably have the same issue with your medicines at Novo Nordisk, that what appears to be a simple film is made up of different and sometimes very different polymers. It can be contaminated plastics. It can be also mechanical recycling. If you look at PET bottles, rule of thumb, you can mechanically recycle it 8 times, and then the quality, the technical quality of the material has gone down so much that you cannot use it anymore in real world applications. So that is one point, and then the others are how to get that, and you've seen. We are still forecasting. Well, not forecasting in this scenario. We still have 35% of fossil virgin fossil feedstock in 2050, and certainly beyond 2050 we need to reduce that further. And then it's a lot about. It's now difficult to say. What can be there to further reduce that 35%, but it's probably going to be a combination of the same levers that we have identified before. So making recycling more efficient in terms of maintaining carbon in the loop. It's about biomass as a source of new virgin carbon. It's about using captured carbon, and what we have assumed here in this scenario is practically availability of captured carbon from industrial processes. We're not talking about DAC, direct air capture, which is also being discussed and may have a crucial role for potentially even reducing CO2 concentrations in the atmosphere in the long run. So this may be another source then of carbon to produce plastics in the long run.
Thank you. Yes, it's complicated.
Sorry. Yes, but thank you very much for your very efficient and very great reply to this. Are there any other questions? Otherwise, we will share the presentation afterwards, but also we are recording so you can revisit. But if you have any questions, please address them afterwards, either to us or maybe even to Alexander directly. So next in line, we're joined by Jesper Bøhlund, the material specialist from Novo Nordisk, and he will share valuable perspective of the use of bioplastics in the health industry. Please, Jesper, share your screen, and we are looking very much forward to listen to you.
Thank you, Susanne. Yeah, great, and thank you very much for the invitation. I'm, as it says, Jesper Bøhlund, and you're welcome to email me afterwards if you have questions that we didn't manage to answer. And also, what I can share today is the story of a project that we have been doing for the last 4 or 5 years, and that we will continue on for the next foreseeable future at least. So it's not a great overview of bioplastics in the healthcare industry, I'm sorry, but it's a practical example, and I hope because we have learned a lot from it, and I hope that it can be an inspiration to others. It started quite some years ago where we were looking at could we find some alternatives to the polypropylene that we use for our injection pens and for packaging. And our eyes fell on PHA because PHA is a very promising and diverse class of materials. I have prepared a couple of highly condensed slides about PHA. So PHA is an abbreviation of polyhydroxyalkanoates. And well, basically it's the way that many bacteria store energy and carbon. Just like we store it as fat in mammalian bodies, they store it as these polyesters. The thing is that these polyesters are thermoplastics, so they are just like plastic, but they are really a biomaterial. You can think of it as just as cellulose or paper, something that is biological in origin and can go back to biology. So it can be also the food source for the same bacteria. But the difference is that where cellulose and many other biomaterials are really hard to process in industrial processes and high volumes, PHA has this advantage that it can be a drop-in. You can process them exactly the same way, exactly the same equipment as we use for the polypropylene today. And maybe the video actually works, yes. So what we see here is a multi-cavity polypropylene production tool making 8 caps, and it's this tiny part, 8 caps at a time, which we need in order to make, when we want to make a high volume production, we're talking millions of parts, and that's simply needed in order to reach all the patients that we serve. And that is a huge achievement to us. Doesn't look like much, but we can actually do this with the PHA that we have developed during the last 2 to 3 years. Now, injection molding is not the only process that we have been investigating. We have also been looking into blow molding of bottles, and that is because a lot of tablets come in bottles, and we use, therefore, a lot of bottles to serve our patients. And that small sequence was a machine ejecting 6 injection blow molded bottles made in one go, and then the table rotates and 6 new bottles come out. And we can do this at even higher efficiency than we can do with polypropylene. We can do it approximately 20 to 25% faster, which the people owning the machines are very happy about because it means higher output from the same investment. We've also made, in the bottom right corner, you can see what is called a cartridge holder. So it's a tiny component. I think I have one here, which is quite complicated and has very intricate details, because these details, they are the mechanical coding for what kind of medicine is inside. So you cannot attach a wrong medicine to a wrong engine and thereby dose your medicine in a wrong dose. So it's very important that they can replicate these tiny features and that they are strong and robust. And we have also made these, and our injection molding people were really amazed that we could do it, because 2 years ago we couldn't. We could only get something out of the mold that had mechanical properties like a cheese biscuit. So it didn't work. But now, after 2 years of development, it actually works. So the great thing about these, the great thing that I promised about the PHA is that they are stable when we put them on the shelf and when we put them in the hands of patients. Think about it as the books you have on the shelf. At least in my time, we used to have books, but a lot of young people don't know them. But books are a great example. They are made of biomaterial, but they don't degrade or disappear just because we store them on the shelf. They stay stable because there's no moisture, there's no bacteria, there's not a lot of heat, only 20, 30 degrees. So basically, they are stable in those conditions. But if they should end up in nature, there will be moisture, there will be bacteria. It's impossible to have PHA create microplastics because it's simply food for the bugs. So it ends up being turned into biomass, bacteria that get eaten by other bacteria, that get eaten by small bugs, that get eaten by birds. You know how the ecological system works. And I think that is the cool thing about PHA. We can use it as we use plastics, but if it should leak into nature, it actually won't cause any harm. Of course, we would like to keep it in the loop because we have invested time and energy in creating the PHA, so we want to use it as many times as possible. I've created a very brief overview of the differences as I explained them to management when I asked for funding for this project. And I tell them that the conventional plastics have a lot of drawbacks. They are already aware of those, that the feedstocks are limited, and we need to cut off the transportation of carbon atoms from underground to the atmosphere. And that's basically what's happening. We have the problems with pollution, a lot of additives, antioxidants, stabilizers, lubricants, all the tiny additives that are in plastics, they leach out into the environment. Many of them are not really healthy. And we have the microplastics ending up everywhere. Also, in the production of plastics, we use a lot of hazardous chemicals and high pressures, high temperatures. It's quite dangerous to be around a chemical plant making plastics. We see once in a while, we see accidents and things leach out into the environment, and it's just, bad stuff leaching out. We have a relatively high carbon footprint, but I admit the costs are low. It's cheap. It's cheap to use the conventional plastics. And the processing energy, I have put it to medium, and it varies widely among plastics, but it's just to highlight that we have now made studies and created the data showing that we can run faster with PHA and we can do it at a lower temperature. So we can save energy and we can also make more parts. The drawback of the PHA is still the cost. We need to invest in development and building up production capacity. But we have seen that when we start reaching pilot-sized fermenters for making the PHA, and that is 10 cubic meters, it's not huge tanks. They are pretty big, but it's not like, then we actually start to reach competitiveness. And competitiveness means that if a polypropylene costs around 10 kroner, 15 maybe, then we can make the PHA to around 30 to 70 kroner. And that will also eventually come down. All experiences say, I cannot say how it will, but I'm sure that we have good things ahead of us. So yes, I see the bioplastics, e-plastics, the whole circular plastics, they are a great step forward. And we should definitely use that also. I do have a bit of difficulty seeing it as a long-term solution because we still struggle with some of the pollution problems. However, I think that there's a good place for both these technologies. And you could imagine that the PHA components that we have made, when they end up as waste, they could become the carbon source to refuel the plastic circle. Maybe if it could be acknowledged as a sustainable biosource, who knows? Now, why did we do this? We did it because we have a Novo Nordisk strategy saying we want to reduce our use of plastic. How do we want to do that? We have 3 main tracks, and the first one is about reducing the consumption. That is by changing into not so much single-use plastic items wherever it is possible. And if you're on a lifelong treatment, you don't need to throw away the injection device every time you have taken an injection. You can actually design systems that can be used again and again. But in many areas in the healthcare, we really like single-use stuff because of safety. It is simply, we are certain that this is sterile, this is brand new, it's not contaminated. So we will never get totally rid of single-use stuff in the medical area. And therefore we have the idea that things that we then do make of plastic, we should change them to a sustainable way of getting the plastic. And that could be circular plastic, or it could be our PHA biomaterial. And we want to do that by driving innovation with startups, smaller companies, universities, people who have all the exciting and great new ideas. Many of them are in the field of industrial biotechnology, and we have some insulin people who know about biotechnology, and there's a good synergy. Though Novo Nordisk is a big company to operate with, it is actually doable, and that's what we have been doing for the last 5 years, working with a small startup that came with the technology for making the PHA. And then we will invest in take-back systems to get help the waste handling industry to actually get our medical waste back and find some way to circle it back into the system. Yeah, this is the management slide for why is it that, what are the visions about this whole PHA thing? So that we want to make it, of course, sustainable and in creating a circular flow of material. We want also to be scalable so that we can push it out to the regional places. If we produce the medicine in China, we should also make the packaging in China and the delivery system. So it's easy to push it out and implement it elsewhere. This is a simple sketch of what it looks like. So in the blue factory, that's Novo Nordisk. We produce a lot of insulin, and this insulin is made in yeast cells. And we harvest the yeast cells, take out the insulin, and then we have this slurry of dead yeast cells. So we will send that to the PHA producer, the one who makes the raw PHA, and we'll send the rest of it directly to biogas production. That's what's happening today. We'll just tap into that waste stream. That raw PHA producer will ferment our yeast waste and create the raw PHA. That needs to go, just like traditional plastics, to a compounding, mixing it with additives. We use bio-based antioxidants and lubricants. And then we'll move that on. So now it's called a formulated resin. move that onto a converter who makes bottles or closures or other things for our products. And then it comes back to us, and we use it to deliver the insulin or whatever medicine it is that we're making. This is a little bit more detailed, and the takeaway message from this is we're not doing this alone. So in the first step, taking the yeast waste and transforming that into a raw PHA, we are collaborating with a Canadian startup called Launch. We're collaborating with FermHub, that is a Lighthouse Zealand project, or actually it's a startup placed close to Kalundborg, where we have our fermentation. And then we have DTU and Center for Biosustainability also working on developing and refining and doing basic research into these fermentation processes. Of course, we want to increase the efficiency of those to get more, as much material out of it as possible. On the compounding side, we are working with another Canadian startup called NextGen Polymers, who have a lot of experience in PHA materials and knowing about how to process them. And a Canadian university, Lambton College. And then, of course, we have DTU, or of course, I say we also have DTU, the Polymer Center at DTU, involved in formulating and making basic research and understanding the materials. And then we have also a relatively small producer called Krebs & Co., situated here close to Hillerød, where I'm sitting. And he's a converter who has also a lot of experience in PHAs. He's making coffee cups and other stuff. And he is helping us to develop a pill bottle. That is our first demonstrator to make a pill bottle that can be used for our own tablets. So what I have been forced to take out here is how much yeast waste do we actually have at hand. And since it's directly coupled to how much medicine we make, I can't show you the exact numbers, but I can say we are in the range of hundreds of thousands of tons. So it's a lot. And just for, just to create a little bit of perspective, if we get 17,000 tons out of these several 100,000 tons, we can make 60 million pill bottles. That's a lot of pill bottles, and it's definitely enough to cover our needs, at least for the closest foreseeable future. And Krebs, that's a small converter, he can make up to 90 million bottles. So we're in a pretty good shape to actually make it happen. Then we envision that after the bottle, we could develop more and replace more of the single-use items. For instance, that small syringe, it has this flange and the piston rod that you push on. Why not make those out of a material that is not based on fossil fuels? We also have other cartridge holders. Hopefully one day we could replace the blister packs. That would really mean something, that we could get rid of blister packing. But there's a whole range of single-use items that I think are a good idea to look at, because we take something that is waste, we transform it into a material, and if it then becomes waste again, well, we haven't really lost something that we wouldn't have lost otherwise. Downstream processing, there's a question to that. Yes, currently, and that's what many people know, is that in academia, we have been using solvent-based purification. So we would take this slurry of biomass and extract it with dichloromethane or chloroform, and then isolate and do research on the PHA. That's of course not feasible in an industrial setting. So we're doing we take the water-based slurry of PHA and biomass, we digest it with enzymes in a watery solution, and then we use washing steps with water to remove the biomass, and then we only have the PHA left. So we have a strong focus on creating and upscaling the downstream processing in watery and benign processes, so that we avoid solvents, we avoid high temperatures, we avoid pressures, keeping everything at benign conditions. This is what we'll do for the next couple of years. We will continue developing the biological processes, the fermentation and the downstream processing. We will scale it up. Currently, we are targeting, we have made fermentations in 30-liter scale. We are going to do 1,000 liter, 1 cubic meter before the end of the year. And then next year, we will go into 5,000 liters. And when we reach 5,000 liters, that's when we start to get material enough to actually really do a lot of material research into this, because then we start to get hundreds of kilos of material out. This means that the polymer compounding will also be continuing, and we will transfer. What we have been doing so far is to purchase material. Now we will replace the purchased material with our homemade yeast waste-based PHA. So we had to do that in order to get things rolling, so we are ready for actually making bottles. Which means that the bottles I proudly show they are made from commercial PHA, I admit, but next year they will be made of our own homemade material. We'll also need to continue developing that the application itself. Maybe we can build in a cool feature that can make it patentable. Who knows? Maybe we'll just make a standard bottle that fits on all production lines in the whole world. That's still work in progress. Another thing is that we will start to approach the authorities and have a dialogue with them about how do you see. Of course, we'll provide the same documentation as with fossil plastics, and that basically we have to document that it's not harmful to the user to touch the bottle, and it's not harmful for the tablets to be inside the bottle. And I'm convinced that we have done, of course, mitigating experiments and skunk tests and trials. We're quite convinced that we can manage to create that documentation. But we will also need a dialogue with the authorities so that they feel they understand PHA and what PHA does to the tablets and to the patients. Yes, a lot of speaking, and if you have any questions, you're welcome to ask them now or write me, and the slides will be shared, except for the one with the strategy. That's yeah.
Thank you so much, Jesper. This was congratulations with this fantastic project, and it seems that there's a bright new future, not only for bottles, but for other ways you can apply this PHA to other of your products. So we have time for a few questions, and in the chat, Rashid is asking, what form of DSP is foreseen and purity of the PHA expected for the application?
Yeah, and we target, as the starting point is targeting the same purity as the commercial available materials, but at the same time, as we do material research and development with DTU, we will look into what kind of impurities are there, what do they do, and how much is needed. So we could just specify it must be 100% pure, and that we would spend a lot of money on the downstream processing. But on the other hand, if we step back and say, we don't bother, we don't spend any investment in the downstream processing, we'll get a material that is brown and smells funny. So we have to find the right place there, that it's pure enough so that it's safe to use, it's easy to process, but on the other hand, not overdoing it. And that is the work that we are going to engage on for the next 2 years. We have been working on that for a year now, and we'll continue that in the next 2 years.
Thank you. And Louise, please, you have a question. You are allowed to speak.
Thank you, Susanne. Yes, but I was just wondering, in Food and Biocluster Denmark, we support a lot of companies that are working with, fermentation processes to produce other products. From what you have experienced with your project, do you think that this is something where there's a huge potential also for other, microorganisms and other like fermentation broths left over? Like, what do you have any insight on that?
I feel that in Denmark we have a huge head start. We have a really good position that we know a lot about bioprocesses. And now that we are getting these pilot plants that bridge the gap from small 250 milliliters experiments at the university to a 10,000 liter. They are currently installing a 10,000 liter fermenter at Fermhop Zealand. That will really bridge the gap, because when we get to 10,000 liter, that is, I mean, we will be able to make enough PHA to serve our need for material for bottles in a 10,000 liter fermenter. So yeah, there's so many opportunities, and there's so many learning opportunities. We can really start a lot of research and get a lot of new students and PhDs and researchers into that area. There was a question about regulatory compliance, and we handle that by looking into USP 671, which states that the materials need to be safe and not cause leachables that change the tablets. So what we will do is to create a material that complies to USP 671, and then we will engineer a tablet container that also complies to the USP. I think that's 661 and 661-2 or something. We have a primary packaging development department that knows everything about how to design and what kind of documentation to provide. So we will make sure that we are just as compliant as current fossil bottles.
Super. One last question to Jesper. Otherwise, as he said, you're welcome to write either to us or to him directly afterwards, and we will share the presentation, of course. This is great, and it also proved that you can't do this even though you are a large company, a huge global company. You have to collaborate with both small and medium-sized companies, but also universities and so on. So if anything, please contact Food and Biocluster Denmark. We can deliver. Anyway, that was a little sidekick. Sorry. We will move on now. We will move on to hear something from our result and key takeaways from our co-creation workshop in the B-Trust project. And to do this, please welcome Annie Simonsen, who is the Senior Innovation Manager, and she will present what we have been discussing in this super exciting workshop we have held or organized. Oops, there you are. So Annie, please, the floor is yours.
Thank you so much for that. And want to start with those fine presentation from Alex and from Jesper. I find that really interesting myself as well. So very nice. Okay, let me start with the consumer and the co-creation with both consumers and with the industry. So although benefits have been widely demonstrated, achieving a broad public acceptance and implementation is proving difficult due to consumer perceptions and concerns, especially when we are talking about controversial areas such as vaccinations and genetically engineered foods. Consumers are reluctant to adapt them. We have invited consumers and industry to participate in 2 co-creation workshops in the months before now, to know if this is also the case with the bio-based materials. So we have had, we started with 1 consumer co-creation workshop. We had 16 participants, and that's on purpose, that we have a relatively small group to make sure that we can discuss and everyone can be heard. We were focused on having a group of ordinary people, you can say, the people you would meet in the supermarket. So we have recruited with a focus on gender, their age, and their occupation. With the industry workshop, we have invited 2 large companies and It says here one SME. It's actually two SMEs and one organization with more than 400 members. So let me share some of the key takeaways. We start with the consumer part. The workshop was organized by Food and Biocluster Denmark, so it's the participants have been Danish consumers. And here was explored perception and future possibilities of bio-based materials and biotechnology. It was structured around discussions, association exercises, and scenario-based reflections. So that was simply to bring the consumers on board in the terms, our choice of terms and technology and those things. They can't just walk in from the street and have this question put in front of them. So we kind of warmed them a little bit up, try to bring them into the right track. Not that we wanted to persuade them to give specific answers, but simply to put them on board in the ship. So we had some main discussions points, definitions and perceptions of biotechnology, bio-based materials and chemicals, and fossil-based counterparts were explored. We divided the participants into 3 groups to have them reflect different perspectives. We suggested some groups and they choose which one to enter themselves. So they gave their thoughts on key terms, revealing unique viewpoints from each their group. So they discussed biotechnology, and the views were different. One group had a focus on innovation, and one had a focus on economic strategies, and the third one on ethically complex issues when they discussed this. When we discussed the bio-based materials, it was seen as sustainable by one group. Another one had a focus that it would be industrial viable with some trade-offs, and the third one was focused on environmentally preferred. It was environmentally preferred, but underused. They didn't see that in their day-to-day life. The bio-based bio-based chemicals were perceived as promising, but poorly understood, with concerns about the transparency and toxicity. And the fossil-based materials, they were generally recognized as non-renewable and polluting. I can share with you when we asked for a very start how many of you understand the term fossil. It was only 1 out of 16 participants, and we were a little surprised about that. In the future focused session, the consumers were introduced to sustainable biotechnology solutions. The complexity of the topic and the need for more transparent communication to broader audience were highlighted. Later, the consumers were introduced to scenario-based reflections, where it was discussed what the potential consequences of a world without plastic and synthetic materials would be. Here, the participant pointed out functionality, environmental impact, and practical functionalities or practical limitations. They consider the total elimination of the products as unrealistic, whereas a gradual reduction and solution were supported. So bio-based materials and biotechnology hold great promises, but the success depends on innovation, efficiency, and widespread awareness. A sustainable future would require a collaboration between industries, policymakers, and the public to ensure these technologies reach their full potential while at the same time minimizing the risks. Other key takes away, I have divided one of them on the groups. We have defined the name of the consumer groups, the optimistic innovators, and the pragmatic industrialists, and the critical environmentalists. So the first group, they see biotechnology, bio-based materials, and biochemicals as future-oriented solutions, emphasizing sustainability, affordability, and technological advancement. However, they acknowledge challenges like regulation, land use, and motivation for large-scale adoptions. The pragmatic industrialist group, they take a practical approach, recognizing the benefits of bio-based materials and bio-based chemicals, but also highlighting economic safety and supply chain concerns. So the skepticism exists in connection with transparency, quality, and environmental trade-off. Transparency is in general quite important for them. The critical environmentalists, they focus on ethical, environmental, and systemic challenges, advocating for better biodegradability, regulation, and public awareness. Concerns about greenwashing, toxicity, and economic interest drive their cautious stance. A few other takeaways is the balance of progress and responsibility. Biotechnology is a powerful tool, but it requires careful management to avoid unintended consequences. Ethical, economic, and environmental consideration must guide the development. That's really important for the consumers. Challenges in adoption. Scaling production, ensuring transparency, and addressing skepticism remain significant hurdles. Public awareness and regulatory framework must be improved to foster trust. The transition, a transition, not an overnight shift. I think they all realize this is complicated and it will take some time. So while eliminating fossil-based material is unrealistic, gradually adoption of sustainable alternatives supported by innovation, waste management, and policy incentives is the path forward. To successful transition to a bio-based economy, cross-sector collaboration, transparency, and public engagement are essentially. So bridging the gap between scientific innovation, everyday understanding will be key to unlocking the potential of biotechnology and bio-based solutions. So that was the overall conclusions we made out of the co-creation workshop with consumers. And then we moved on a little later with the a focus meeting with the industry, with the 5 participants, the 2 big companies and 2 small companies, and an association with representing more than 400 members. So we asked them to rank what are the pros and what are the cons in this area for you. For the pros, the first one, the top priority was lower climate footprint. So bio-based materials have the potential to reduce CO2 emissions compared to fossil-based plastics significantly. That was the top priority. The second one, reduction in fossil material consumption by using bio-based materials. The reliance on fossil resources can be decreased. Third, the health benefits was important. These materials can lead to less exposure to harmful chemicals, which is of course beneficial for the health. I remember Jesper just mentioned that with the production as well. The consumer demand, there's a growing consumer demand for greener products, which bio-based materials, of course, can fulfill. Environmentally friendly production, the production process for bio-based materials can be more environmentally friendly. And local production was the last one. There's a potential for increased local production, thereby reducing dependence on global supply chains, and as Jesper mentioned, even better using your own side streams. So asking about the cons and having the ranking here, material properties came up as the first one. Bio-based materials often lack the necessary properties for specific applications, such as durability and mechanical strength. I think you mentioned the cheese cracker, Jesper. Regulatory challenges is the second one. Navigating the regulatory landscape for bio-based materials can be complex and challenging. So we have high research and development costs, significant investment in research and development, as well as establishment of new production facilities are required. For supply security, ensuring a consistent and reliable supply of bio-based materials can be difficult. If you look at some of the old industries, the fossil chemical industry, often you have not only two suppliers, but several suppliers as optional when you consider your procurement strategy, and that is of course a little different here. Fifth, competitiveness. Bio-based materials can be more expensive than their fossil-based counterparts, affecting the competitiveness of the products, but also of the final product, of course. Greenwashing accusations. There's a risk of being accused of greenwashing if the environmental benefits of biomaterials are overstated or considered overstated. And I think the risk is even that the consumers would not understand what is really communicated here. And as number 7, consumer acceptance is listed. Gaining consumer acceptance for new materials can be a challenging task. And finally, end-of-life uncertainty. There's a lack of recycling options and uncertainty about the end-of-life process for bio-based materials. It's a young world here. So if we look at the general remarks from the session with the industry, the bio-based materials industry is relatively young compared to the traditional fossil-based sector and faces, therefore, of course, numerous challenges. These include determining the end-of-life products, developing valid acceleration tests, and conducting solid research to bridge the gap between old and new material. It is emphasized that in some cases, a focus on good materials and products should maybe be replaced by the pursuit of perfect ones. You can go for good materials and good enough for a start, and not necessarily the perfect one for a start. Additionally, explaining new products and technical terms to consumers can be difficult. Ethical concerns such as competitive competition with food stocks or PLA development can be elevated by focusing on side streams from food production, like fiber streams from sugar cane was mentioned. You want to use it primarily for the for food, but still you end up having a side stream of fibers at the very end. And if you can use that for other purposes, for instance, PLA, that is a very good option. Overall, while there are significant advantages to using bio-based materials, there are also notable challenges that need to be addressed to fully realize their potential. So that's of course not so surprising. I think that is all from our 2 workshops. So thank you for letting us share that with you. I'll stop sharing the screen here.
Yes, thank you very much, Annie. Are there any questions from this a little bit comprehensive, very intensive 2 workshops we had? And if you have any questions, please either use it in the chat. You're also welcome to raise your hand and speak if you want.
I can say we have had more co-creation sessions with consumers with the different topics. And it's really clear to us that the consumers, they would like to have transparency. They would like to be able to see what is going on within this field. And you can say that is definitely fair enough to ask for that. So for the Danish consumers, it was very important to have this transparency. In some cases, there were workshops in Spain and Belgium as well, and they were not as concerned about that. Jesper, you have a question?
Yeah, thank you very much. It's very interesting to hear what the consumers actually say. And the thing about making not having perfect standing in the way of the good, I think maybe as a materials guy, I often it should be perfect. Do you really think would they be more accept? I mean, if assuming that we communicate openly, that we give them this new, I don't know, cap or bottle or whatever, and we say, yes, it's not perfect, but it's better than the one we had before. Would that be do you think that would be a way forward?
We haven't asked them specifically, but personally, I think that would be a way forward.
I
think.
Sorry,
yeah.
Annie.
Go ahead.
Now, when we compared it to the workshop we had with consumers concerning food and various, like cell factories and so on, they said, okay, bring us some tests, trial test of the product so we can see, does it fulfill the same taste, structure, and so on. Well, what is it? They were very curious about learning what is all this new thing. Show us, and let us try it. And then, I think it's very important to keep the dialogue. So if you have the finished product and then you put it on the market, maybe the consumer do not like it. So involve the consumers. I think you already, before we started, mentioned that you had a consumer focus group or something like that. So I think when you are on the front of new frontiers, I think it's important to stop up, try it. Is it good enough? Will the consumer accept it? And then move on. Maybe you're doing it already, but we actually, I know we had a few, only 16 on that workshop, but still it was interesting to learn from the group that I was in that, we would like to try it, but show us first. So anyway, Louisa, you also had a question?
Yeah, just to add to what you were saying, and I think Annie mentioned it partly as well, what we found was that, with information, the openness was severely promoted, or the more they knew, the more accepting they were. So it's very much about finding a way to provide your clients or the consumers with information about what this is and why you're doing it. And I think a lot of skepticism comes from uncertainty and lack of knowledge and transparency about how things are produced and why, but also to some degree lack of knowledge about the alternative. I think it was really very surprising to me that actually, that while you may know what plastic is, you don't know what fossil means. So, like when you give that communication to them, you have to make sure you start like really from scratch, and not assume that we all know what fossil means, because clearly that wasn't the case. These were, teachers, farmers, social workers. They were not people who have never gone to school. And nonetheless, they did not understand what the term fossil was. And we hadn't even prepared for that in the workshop. It just became clear in the discussion. So at one point I was like, can you raise your hand if you actually know what that means? And only one person raised their hand. So it's all about that information and transparency and making that very clear to your customers and to the consumers.
Also, if I may add, some groups also during these masterclass had a little skepticism that, now the big company, the corporates are coming, they're taking over this field as well. So there was a concern of the social or economy impact on what this will mean as well. And in some cases, they even, were afraid of the global south and global north, if you may say so. So there was also a concern that was shared in Belgium as well, that the big companies are coming again and taking over. But okay, I'm exaggerating a little bit. But
I think, Susanne, it came out of the concern. This is so technical.
Yeah.
Does a small company have a chance in this field?
But I think now that you mentioned, Jesper, that you are collaborating with the small and medium-sized companies, so I think that's also a good communication. We're not doing this by ourselves. We are doing this in collaboration with the whole value chain, and the big and small and university science and industry are meeting here. So I think that's also a good takeaway. That's my personal opinion. Sorry. So yeah.
I think maybe it is a bit by coincidence that we don't do it ourselves, but it's also, we are a medical company, and my management made it clear, Novo Nordisk AS is not going to produce plastics or PHA or any other materials. So I had to find some collaborators and then Novo Nordisk AS, I can drive them to invest in the development and so on, but I also have to provide them with a plan for when do the small startups take over.
Yeah.
But maybe that's actually a good thing.
Yeah, I think what we learned from the last workshop was also that the companies, the industry can't do it by themselves individually. And what we also heard Alex said today, Europe, it's not only the companies, it's also maybe the EU Commission should put more money into developing the various biotechnical solutions, and they're looking into it. And this is one of these projects that we are trying to bridge the trust and unlock the trust, so to speak, the potential. So anyone more comments? Otherwise, I will just share the last few slides. Doesn't seem to be the case. So I will just do a little promotion for the final masterclass that we have, and it's already next week, the 25th of June, where we will have a conclusion and lesson learned mainly from the workshop, but surely also a sneak preview of the co-design measures, the methodologies that we use for the co-creation session, and of course also, as I said, the result on trust and acceptance. So you can sign up, you already listed on the forum, so you can sign up for the next, and we will promote it very shortly. I'm just, it's a little bit slow, but if you missed and you are more interested in learning what we've done, we have recorded all of the master classes, and we actually have a YouTube channel. So if you go to the community platform, then you'll be able to see all these master classes. So I think we will wrap up for today and say thank you so much for your participation. Great speakers showing insight into these very super highly actual topics, and we thank you for your engagement as well, for the questions, and hopefully see you on the 25th, or please, if you have any questions, you can write to us and we can reply or send the question further on. So again, last chance to raise your hand to say anything, then it's now. Otherwise, we are right on time and almost only a few minutes over time. And then thank you again. And this is it for today. Thank you.
Thank you.
Bye-bye.
Thank you. Bye.